Hello, Accelerated Chemistry. This is Mr. Spurk, and this is your Chapter 19, Section 2 notes on hydrogen ions and acidity. On occasion, the collisions between water molecules are energetic enough for a reaction to occur. So two water molecules might bounce into each other and collide, and we might get a hydronium ion and a hydroxide ion, which means that one of the waters would have given up a proton, or a hydrogen. A water molecule that gains a hydrogen ion becomes a hydronium ion, H3O+. A water molecule that loses a hydrogen ion becomes a hydroxide ion. The reaction in which water molecules produce ions is called the self-ionization of water. In an aqueous solution, hydrogen ions are always joined to water molecules as hydronium ions. In pure water at 25 degrees Celsius, the concentration of hydrogen ions is only 1.0 times 10 to the negative 7 molar. The concentration of OH minus is also 1 times 10 to the negative 7th molar because the numbers of H plus and OH minus ions are equal in pure water. Any aqueous solution in which the concentration of hydrogen ions and the concentration of OH minus ions are equal is a neutral solution. The ionization of water is a reversible reaction, so the Chatelier's principle applies. For aqueous solutions, the product of the hydrogen ion concentration and the hydroxide ion concentration equals 1.0 times 10 to the negative 14. So, H plus OH minus equals 1.0 times 10 to the negative 14. The product of the concentrations of ions and hydroxide ions in water is called the ion product constant for water. So this should say multiplied by, that should be a multiplication symbol. It should be an X because it is the product. So they're multiplied together. So the product of the concentration of H plus times the concentration of OH minus equals 1.0 times 10 to the negative 14. So let's talk about acidic solutions. So let's look at hydrochloric acid being dissolved in water. We know that we get H plus ions and Cl minus ions. The hydrogen ion concentration is greater than the hydroxide ion concentration. A solution in which the concentration of H plus is greater than the concentration of OH minus is an acidic solution. For basic solutions, it's just the opposite. The hydrogen ion concentration is less than the hydroxide ion concentration. A basic solution is one in which the concentration of H plus is less than the concentration of OH minus. So we can use the ion product constant for water and solve for different concentrations. So if the concentration of H plus in a solution is 1.0 times 10 to the negative 5 molar, the solution is acidic, basic, or neutral. Let's figure out. What is the OH minus concentration of this solution? So we know that our ion product formula is Kw equals the concentration of H plus, and remember this is multiplied by, not addition, times OH minus concentration. So we know that Kw is always 1.0 times 10 to the minus 14, should be a minus 14, equals the concentration of H plus, which we know is 1.0 times 10 to the negative 5 molar. And we're solving for the hydroxide ion concentration. So we divide by 1.0 times 10 to the negative 5, and we determine that the concentration of OH minus is 1.0 times 10 to the negative 9 molar. So if we look at the concentration of H plus, which is 1.0 times 10 to the negative 5th, and compare it to 1.0 times 10 to the negative 9th for hydroxide, we can determine that this is an acidic solution because the concentration of H plus is greater than the OH minus concentration. So we're going to talk about the concept of pH. The pH of a solution is the negative logarithm of the hydrogen ion concentration. So pH equals the negative log of the concentration of H+. So just as a quick demonstration, for a neutral solution, the pH is equal to the log of, at a neutral solution, we have 1.0 times 10 to the negative 7. And when you punch that into your calculator, the pH of a neutral solution is 7.00. So a pH that is neutral. A pH less than 7 is acidic, and a pH greater than 7 is basic. So let's calculate H plus from the pH. The pH of an unknown solution is 6.35. What is the hydrogen ion concentration of the solution? So again, our equation for pH is the pH is equal to the negative log of the H plus concentration. We know that the pH is 6.35, and we're trying to determine the H plus concentration. So we need to do a little bit of algebra. So what we're going to do is we're going to divide by that negative 1. So we have negative 6.35 equals the log of H plus. And this might be a new concept for some of you. Logs are base 10. They're based on 10. So to get rid of a log, we use base 10. So we have 10 raised to the negative 6.35 power equals 10 raised to the log of H plus. So what this does is we can punch this into our calculator on the left-hand side, but on the right-hand side, it eliminates that log, so we're left with just the concentration of H plus. So when we punch this into our calculator, H plus equals 4.45 times 10 to the minus 7. Well, let's rewrite that there. Times 10 to the minus 7 molar. So that is how we can work backwards from knowing the pH and try to determine the concentration of H plus. So we can also calculate the pH if we only know the OH minus concentration. But if you remember, the pH is equal to the negative log of the H plus concentration. So using the OH minus concentration, we need to determine the concentration of H plus, and then we can calculate the pH. So to do that, we're going to use our Kw expression. And rearrange for the H plus. So H plus equals Kw over the OH minus concentration. So let's plug in our values. H plus is equal to, Kw is always 1.0 times 10 to the negative 14 divided by 4.0 times 10 to the negative 11. So our H plus concentration is 0.00025 molar. And now we can calculate our pH. pH, again, is equal to the negative log of the H plus concentration. So pH equals negative log of 0.00025. And when you type this into your calculator, you get a pH of 3.60. So we also have these things called acid-base indicators. An indicator is an acid or a base that dissociates in a known pH range. These indicators are often colors based on the pH conditions. So if you look along the x-axis, we see the different pH values that range from 0 to 14. And based on the indicators along the y-axis, if those are within our solution and we go through a pH change, we will see a color change. And that way we know what pH we're at. We can see where our solution is changing pH. So an indicator strip is a piece of paper or plastic that has been soaked in an indicator and then dried. And we've used pH papers in some of our labs before. We've dipped the blue pH paper in, and if it turns red, it's acidic, and vice versa for basic solutions. So below, we actually have some natural pH indicators. If you've ever seen these flowers out somewhere, they're called hydrangeas. And when they are grown in acidic soil, they have blue flowers. But when they are grown in basic soil, they have pink flowers. And that is just a naturally occurring acid-base indicator. So we can also use pH meters to measure pH. A pH meter is used to make a rapid, continuous measurement of pH. Typically, they're accurate within 0.01 pH unit of the true pH, and probes or meters are often easier to use than a pH strip. Also, these give you a value, whereas a pH strip just tells us is it acidic or basic. Alright, so in review, for aqueous solutions, the product of the hydrogen ion concentration and the hydroxide ion concentration equals 1 times 10 to the negative 14. A solution with a pH less than 7.0 is acidic, a solution with a pH of 7 is neutral, and a solution of pH greater than 7 is basic. Either acid-base indicator or pH meters can be used to measure the pH. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.